Okay, let's continue our lecture. Now I'm going to speak about some simple examples of functionals. I want to speak about some famous problems in functionals. Let's start our first example, which named brachistochrone. This example was first presented by Bernoulli at 17th century. Let's first speak about the problem and then about the formulation. The problem is to find a frictionless tooth between 2 points 1 and 2 in a vertical plane such that a body sliding under the action of its own weight goes from point 1 to point 2 in the shortest interval of time. Let's draw a picture. Here is y-axis and here is x-axis. Let me okay, it's better now. Let's see. Okay, let me change the color. It's the direction of the gravity. The gravity is in the opposite of y direction. It's point 1 and it's point 2. We want to find a path from point 1 to point 2. In this path, if we have a mass sliding under this path from point 1 to point 2, we want to have a shortest interval time for example, we have infinite passes from point 1 to point 2. We are going to find an extremum curve which minimize the interval time. Okay, now let's formulate the problem. If I redraw this picture for a small a small part of the curve. This distance is dx and this distance is dy. The length of the path from this point to this point is ds. We can say ds by 2 equals to dy by 2 plus dx by 2. We know that v velocity is equals to ds over dt. This is the absolute velocity of the point. From this formula, we can say that dt equals to ds over v, as we can see in this formulation. And if we can find the total path, the total time, we should we should integral these equations from point 1 to point 2. As I mentioned before, ds by 2 is equals to dx by 2 plus dy by 2. So we can say ds is equals to the root of dx by 2 plus dy by 2, and if we divide this equation by dx, we have integral from x1 to x2 of this function 1 plus y dash by 2 all squared over v d of x. This is the functional we are going to experiment. However, the value of v must be determined as a function of y and x. As we know, the path is frictionless. We can use the conservation of energy, and we can say that the mechanical energy is conservative during the path. So we can say the potential energy plus kinetic energy is always a constant number. So m v1 initial velocity, if m v1 plus 2 I'm sorry, m v1 by 2 over 2 plus mg y1 equals to mv2 over 2 plus mgy. So we can calculate v by this formula as a function of v1, y1 and y. v1 and y1 has definite numbers, and the functional problem is as follows. In the functional problem, we are going to find y of x in order to minimize this functional. And this is one of the famous problems we have in variational approach. And now let's speak about our next problem. Okay, this problem is called geodesic problem. Geodesic problem is a problem, is a functional problem with constraint. In this problem, we are going to find a curve from point 1 to point 2, which has a minimum length, and on the other side we have some constraints. We know that the path must be on a surface g of x, y, and z, and this is the problem. We want to find a path on a surface. This is our surface. The formulation of the surface is presented by equation 225. This is our surface. We have point 1 and point 2 on this surface, and there are infinite passes from point 1 to point 2. In between these passes, we want to find the path which has minimum length, Okay, now let's formulate the problem as I mentioned. In this case, we present our problem as follows. We know that d of s, the length of a small element, is equals to dx by d of s by 2 is equals to dx by 2 plus dy by 2 plus dz dz by 2. If we calculate the roots of this equation, we have equation 2, 4, and this is our next famous problem we usually have in calculus. This is a functional problem with a constraint, with a function constraint. In this course, we will speak about these kinds of problems and how we can solve this kind of problems using Lagrange multipliers. And now let's speak about our last example. Okay. And our last example named isoperimetric problem. Isoperimetric problem is a very common problem in mathematics. Let's first speak about the problem. The problem is to find to find an equation of curve with a fixed length L, which have the greatest area. Okay, so if I want to draw the problem, we have a curve with length L. We want to change the shape of this curve in order to have the greatest area. We can show that the area of this path can be calculated, but by this formula I will prove it in the next slide. We can show that A, the area of this curve can be calculated by this formula: integral of x dy minus y dx. And if we express x and y parametrically in terms of tau, then we can say that dy equals to derivative of y with respect to t multiplied by dt, and dx is equals to derivative of x over dt multiplied by dt. And if we rewrite these equations, we can have a functional in this form. You can see in these equations we have two unknowns, or in other words, we have two unknown functions, and our functional is function of two functions. So we must have two equations to find x of tau and y of tau. I will speak about it in more details in our next sessions. Now let's focus on the title of our examples. In these examples, this is our functional. Moreover, we have a constraint. The constraint is the length of the curve, as it mentioned in the problem. The length of the curve is a constant number L. L equals to integral of ds. We can say that integrals of ds equals, we know that ds equals to dx by 2 plus dy by 2, all of them power 1 over 2. And if we rewrite dx and dy as in a parametric way, we can rewrite our equation in this form. We can say dx is equals to dx over 2 multiply dx dx over d tau multiplied by d tau, and the same for dy, and this is our integral constraint. This is the another type of variational problem. In this problem, we have integral constraint. We will speak about different kind of variational problems in our next sessions, and how to solve these problems using variational approach, and how to find the extremum function of these functionals. For the last part, I want to prove this statement, how we can calculate the area by this formulation. Okay, let me speak about let me speak about a closed curve. We know that a equals to integral of 1 dA. From the divergence theorem, we know that if f is a vector function, we know that integral of divergence of f d of a is equals to integral over the closed curve f dot n d of s, where d of s is the length of an element, and n represents a unique normal vector, normal vector to the curve. We can show that nds equals to dy I hat minus dx j hat. And if we have f as follows, the first term of f is x and the second term of f is y, we can show that divergence of f is equals to 2, and we can say that a or area is equals to 1/2 of divergence of f d of a. We use this term for f and this term for n dot ds. If we use dot product of these two terms, we can show that f dot n d of s is equals to this equation. And how now we can show that how we can calculate the area of the closed curve using this formula. Okay, I think it's enough for this session. If you have any question related to the course, you can have your questions in our next online class. I wish you all the best and hope to see you soon. Bye bye for now.